In chemical kinetics, the order of reaction with respect to a given substance is defined as the index, or exponent, to which its concentration term in the rate equation is raised. For the typical rate equation of form, where A, B are concentrations, the reaction orders an X for substance A, Y for substance B, etc. The overall reaction order is the sum X plus Y plus. For many reactions, the reaction orders are not equal to the stoichiometric coefficients. For example, the chemical reaction between mercury chloride and oxalate ion 2HgCl2 plus C2O42 minus 2Cl minus plus 2CO2 plus Hg2Cl2 has the observed rate equation R equals K HgCl2 1 C2O42 minus 2. In this case, the reaction order with respect to the reactant HgCl2 is 1 and with respect to oxalate ion is 2. The overall reaction order is 1 plus 2 equals 3. The reaction orders differ from the stoichiometric coefficients. Reaction orders can be determined only by experiment. Their knowledge allows conclusions to be drawn about the reaction mechanism, and may help to identify the rate-determining step. Elementary reactions do have reaction orders equal to the stoichiometric coefficients for each reactant. The overall reaction order, i.e., the sum of stoichiometric coefficients of reactants, is always equal to the molecularity of the elementary reaction. Complex reactions may or may not have reaction orders equal to their stoichiometric coefficients. Orders of reaction for each reactant are often positive integers, but they may also be zero, fractional, or negative. A reaction can also have an undefined reaction order with respect to a reactant if the rate is not simply proportional to some power of the concentration of that reactant. For example, one cannot talk about reaction order in the rate equation for a bimolecular reaction between adsorbed molecules. Determination of reaction order. Method of initial rates. The order of a reaction for each reactant can be estimated from the variation in initial rate with the concentration of that reactant. Using the natural logarithm of the typical rate equation, for example, the initial rate can be measured in a series of experiments at different initial concentrations of reactant A with all other concentrations B, C, kept constant, so that the slope of a graph of as a function of then corresponds to the order x with respect to reactant A. However, this method is not always reliable because measurement of the initial rate requires accurate determination of small changes in concentration in short times and is sensitive to errors. And the rate equation will not be completely determined if the rate also depends on substances not present at the beginning of the reaction, such as intermediates or products. Integral method. The tentative rate equation determined by the method of initial rates is therefore normally verified by comparing the concentrations measured over a longer time with the integrated form of the rate equation. For example, the integrated rate law for a first-order reaction is where A is the concentration at time t and at 0 is the initial concentration at 0 time. The first-order rate law is confirmed if is in fact a linear function of time. In this case, the rate constant is equal to the slope with sign reversed. Method of flooding. The partial order with respect to a given reactant can be evaluated by the method of flooding of Ostwald. In this method, the concentration of one reactant is measured with all other reactants in large excess so that their concentration remains essentially constant. For a reaction AA plus BBCC with rate law, the partial order alpha with respect to A is determined using a large excess of B. In this case and alpha may be determined by the integral method. The order beta with respect to B under the same conditions is determined by a series of similar experiments with a range of initial concentration B0, so that the variation of K can be measured. First order. If a reaction rate depends on a single reactant and the value of the exponent is 1, then the reaction is said to be first order. In organic chemistry, the class of SN1 reactions consists of first-order reactions. For example, in the reaction of aryl diazonium ions with nucleophiles in aqueous solution N2 plus X minus Ox plus N2, the rate equation is R equals K, N2 plus, where R indicates an aryl group. Another class of first-order reactions is radioactive decay processes, which are all first-order. These are, however, nuclear reactions rather than chemical reactions. Second-order. A reaction is said to be second-order when the overall order is 2. The rate of a second-order reaction may be proportional to 1 concentration squared, or to the product of 2 concentrations. As an example of the first type, the reaction NO2 plus CO plus CO2 is second order in the reactant NO2 and zero order in the reactant CO. The observed rate is given by, and is independent of the concentration of CO. The second type includes the class of SN2 reactions, such as the alkaline hydrolysis of ethyl acetate. CH3COO C2H5 plus O minus CH3COO minus plus C2H5OH. This reaction is first order in each reactant and second order overall. R equals K CH3COO C2H5O-, if the same hydrolysis reaction is catalyzed by imidazole, the rate equation becomes R equals K imidazole CH3COO C2H5. The rate is first order in one reactant, and also first order in imidazole, which as a catalyst does not appear in the overall chemical equation. Pseudo-first order. If the concentration of a reactant remains constant, its concentration can be included in the rate constant, obtaining a pseudo-first-order rate equation. For a typical second-order reaction with rate equation, if the concentration of reactant B is constant, then, where the pseudo-first-order rate constant, the second-order rate equation has been reduced to a pseudo-first-order rate equation, which makes the treatment to obtain an integrated rate equation much easier. For example, the hydrolysis of sucrose in acid solution is often cited as a first-order reaction with rate. The true rate equation is third order, however, the concentrations of both the catalyst H+ and the solvent H2O are normally constant, so that the reaction is pseudo-first order. Zero order. For zero-order reactions, the reaction rate is independent of the concentration of a reactant, so that changing its concentration has no effect on the speed of the reaction. This is true for many enzyme-catalyzed reactions, provided that the reactant concentration is much greater than the enzyme concentration, which controls the rate. For example, the biological oxidation of ethanol to acetaldehyde by the enzyme liver alcohol dehydrogenase is zero order in ethanol. Fractional order. In fractional order reactions, the order is a non-integer, which often indicates a chemical chain reaction or other complex reaction mechanism. For example, the pyrolysis of ethanal into methane and carbon monoxide proceeds with an order of 1.5 with respect to ethanal. R equals K CH3CHO 3/2. The decomposition of phosgene to carbon monoxide and chlorine has order 1 with respect to phosgene itself and order 0.5 with respect to chlorine. R equals K COCl2 Cl2 1/2. The order of a chain reaction can be rationalized using the steady-state approximation for the concentration of reactive intermediates such as free radicals. For the pyrolysis of ethanal, the Rice-Hertzfeld mechanism is initiation CH3CHO CH3 plus CHO, propagation CH3 plus CH3CHO CH3CO plus CH4 CH3CO CH3 plus CO, termination 2 CH3C2H6. Where denotes a free radical. To simplify the theory, the reactions of the CHO to form a second CH3 are ignored. In the steady state, the rates of formation and destruction of methyl radicals are equal, so that the concentration of methyl radical satisfies The reaction rate equals the rate of the propagation steps which form the main reaction products CH4 and CO, in agreement with the experimental order of 3/2. Mixed order. More complex rate laws have been described as being mixed order if they are approximate to the laws for more than one order at different concentrations of the chemical species involved. For example, a rate law of the form represents concurrent first-order and second-order reactions, and can be described as mixed first and second order. For sufficiently large values of such a reaction will approximate second-order kinetics, but for smaller the kinetics will approximate first order. As the reaction progresses, the reaction can change from second order to first order as reactant is consumed. Another type of mixed order rate law has a denominator of two or more terms, often because the identity of the rate determining step depends on the values of the concentrations. An example is the oxidation of an alcohol to a ketone by hexacyano-4 ion, Fe63- with ruthenate ion as catalyst. For this reaction, the rate of disappearance of hexacyano-4 as this is zero order with respect to hexacyano-4 at the onset of the reaction, but changes to first order when its concentration decreases and the regeneration of catalysts becomes rate determining. Notable mechanisms with mixed-order rate laws with two-term denominators include Michaelis-Menten kinetics for enzyme catalysis, first order in substrate at low substrate concentrations, zero order in substrate at higher substrate concentrations, and the Lindemann mechanism for unimolecular reactions, second order at low pressures, first order at high pressures. Negative order. A reaction rate can have a negative partial order with respect to a substance. For example, the conversion of ozone to oxygen follows the rate equation in an excess of oxygen. This corresponds to second order in ozone and order with respect to oxygen. When a partial order is negative, the overall order is usually considered as undefined. In the above example, for instance, the reaction is not described as first order even though the sum of the partial orders is 2 + = 1. Because the rate equation is more complex than that of a simple first-order reaction,